Hello mathematicians, thank you for joining me today. Today what we're going to do is we're going to go through and try to show that the set of all 2 by 2 symmetric matrices forms a subspace of the vector space of all 2 by 2 matrices. So as we start this problem, what we want to do is remember what are the symmetric matrices. And so we're going to let W be the symmetric 2 by 2 matrices, and we set M sub 2 as the set of all 2 by 2 matrices. Well, we notice that a 2 by 2 matrix has 2 rows, 2 columns, so it's going to be a square matrix. And then furthermore, what we're going to have is we're going to have real entries A, B, C, and D. Now, it's symmetric if the matrix is equal to the transpose of the matrix, where the transpose of the matrix is just, well, instead of row vectors, we're going to have column vectors. So we're going to place all of our rows as columns, and so what we get is A, B, C, D transposes A, C, B, D. Now, if A is equal to A transpose, what that means is that component-wise these are the same. So we need A equal to A. Well, A is always equal to A, so that doesn't provide any restriction. But we also need B equal to C, and so what we get here is that, well, if B is equal to C, that just means that both of these terms need to be B. And so this one again is going to be B. And if we continue, we get, using that, we also have B is equal to B. Now it doesn't provide any more restrictions. And so then if we check D is equal to D, well, that's always true. So what we get is that in this matrix A is a 2 by 2 symmetric matrix if it can be written in the form A, B, B, D. Now what we have to show is that if we take the set of all such matrices, that it's going to form a subspace of the vector space of all 2 by 2 matrices. Now if we recall, a vector space is a set which satisfies some properties, and namely there's 10 different properties we want to satisfy. Now if you want to see a full list of this, I'll provide a link at the description so that you can go to that right up for what a vector space is. But what we were able to do is that we were able to show that things like the set of all 2 by 2 matrices is a vector space, as well as the set of all n by m matrices. So if I fix the size of any matrix, it's going to form a vector space under the usual addition and scalar multiplication. Also, r to the n is a vector space for all n. And so what we get is, okay, we have these are vector spaces, they satisfy properties. But now what we're trying to do is we're trying to figure out, is something a subspace? Well, when we're dealing with subspaces, the nice thing is that we know that we're dealing with a subset. So what are the properties that were satisfied, that needed to be satisfied for a vector space, are satisfied because they hold in the vector space. So instead of having to check all of the properties all over again, what we get is that W will be a subspace of V. That is, assuming that we already know V is a vector space, then W is a subspace of V if for every C and D in the field that we're over, which is generally the real numbers, and U and V vectors in W, we have that C times U plus D times V is again in W. And W is a non-empty subset of V. That is, instead of showing all of those different things for W again, what we have to show is that W is a subset of V, so it does have to be contained in V, and the addition and scalar multiplication have to be defined in the same way. But then once we get that, we have to check, okay, is W non-empty? And then if I take any U and V and W and C and D in my field, if I can take the constant times U plus constant times V, if I end up back in W, I will indeed have a subspace of my original vector space. Alright, as we're working with W, we need to show that it is a subset of our vector space and that it is a non-empty subset. So the first thing we need to notice is that, well, is W a subset of the set of all 2 by 2 matrices? Well, notice that W only consists of 2 by 2 matrices. Therefore, since this contains all 2 by 2 matrices, it contains all 2 by 2 matrices of this form, so W is indeed a subset of the set of all 2 by 2 matrices. Now, to show that it's a non-empty subset, we have to find an example. So an easy example would be, well, let's let A equal B equals C equals 0. Then we get the matrix 0, 0, 0, 0. Notice that this is symmetric because this term is equal to this term. Therefore, this is in W. So we do indeed have that W is a non-empty subset of M22. Alright, so what we're going to do is we need to check that for, in this case, any C and D that are real numbers, we can take any two vectors in our subspace, or what we're checking to be our subspace. That is, we take A and B would be matrices in W. And what we want to show is that C times A plus D times B is again in W. That is, we want to show that this does indeed form a 2 by 2 symmetric matrix. So what I'm going to do here is actually just multiply these out and see what happens. And so what we would get is C times A11, A22 is what I've denoted the entries of A, plus D times B11, B22 is how I denoted the entries of B. So now, if I multiply these, I would multiply C times each of the components, and then I would multiply D times each of the components, and then I would add component-wise. So what you'll notice is that we end up with C A11 plus D B11, and then in the second column of the first row we get CA plus DB, and then the second row first column we get CA plus DB, and then we get CA22 plus DB22. So we do indeed get that. Well, if we look at this, notice that now CA plus DB is equal to CA plus DB. So this entry is the same as this entry. It doesn't matter what these two look like. It just matters that these are the same and we'll make it a symmetric matrix. So therefore, this vector is in the space W of all symmetric 2 by 2 matrices. If we now combine everything together that we had, we saw that W was a non-empty subset of M sub 2, so there was something in there and it was contained in a set of all matrices of size 2 by 2 with the same addition and scalar multiplication. We further saw that if we take any real numbers C and D and any matrices A and B and W, so those would be the vectors in W, then CA plus DB was again in W. Therefore, we have that W is a subspace of M sub 2. Now that we've shown that the set of symmetric matrices of size 2 by 2 is a subspace of the set of all 2 by 2 symmetric matrices, what I want to do now is look at a new set as a subset of another vector space, and I want to know, is it a subspace of my new vector space? So in particular, what we have is the set W, which is equal to the ordered pairs of the form x comma x squared for all x and r. And I want to know, is this a subspace of r squared? So if I want to know that, what I need to know is this a non-empty subset of r squared? And if I take two real numbers C and D and take C times something in W plus D times something in W, do I end up with something in W? To answer the first question, I can note that, well, is W a subset of r squared? Well, notice that this is an ordered pair. If I take a real number x and I square it, I get a real number. Therefore, this is a real number, this is a real number. So this is indeed an ordered pair with entries in R. So this is contained in R squared. Therefore, every element in W is contained in R squared. So we can say that W is indeed a subset of R squared. Now to see that it's a non-empty subset, what we would do is we would pick something in there. So let's let x equal 0. Then note that 0 squared is 0, is indeed in W. So W is a non-empty subset of R squared. So now we move on to the next question is, let's suppose I have two real numbers and I have two vectors in W. What's going to happen if I take C times x squared plus D times y y squared. If I add those together, do I again end up back in w? And so what I'm going to see here is that this is going to become c times x plus d times y is the first term, so cx plus dy, and then I'm going to get cx squared plus dy squared. And what I want to know is, in general, if I take a constant times x plus a constant times y, and I square it, is that equal to this? If it is the case, then this is in w. If that's not the case, then it's not in w. And so what I can do is I can actually look at, say, cx plus dy squared. And if I FOIL that out, I get c squared x squared plus 2c dxy plus d squared y squared. And now if I look at this, c squared x squared plus 2c dxy plus d squared y squared, does that look like cx squared plus dy squared? Well, no, those look drastically different. So what I would think here is that this is not a subspace because it's not going to give me something back in w. So now if I want to show this is true, what I have to do is actually find an example and show that these two things aren't always equal. So in particular, what I would do is just say, well, let's pick an easy example. Let's suppose that c is 2. Then let's suppose that x is 1. Now, if I did this all over again, what I end up getting is that, well, and I should let d be 0 and y be 1. And if I multiply these matrices, I get 2 times 1 comma 1 plus 0 times 1 comma 1. Because 1 squared is 1, 1 squared is 1. If I multiply this out, I get just the matrix 2, 2. So now in this case, I'm taking c times a vector in w plus d times a vector in w, and I'm getting out the vector 2, 2. What I want to know is 2 equal to 2 squared? Well, 2 squared is equal to 4, which is not equal to 2. So we have that 2, 2 is not an element of w. Hence what we have is that when we're trying to show that it was closed under this property here, we notice that we got something outside of there. So therefore, we notice that a scalar times a vector is not back in the space, so it is not a subspace because it is not a vector space. Thank you for watching. As always, I hope you learned something today, and I hope you enjoyed the process along the way. If you did, make sure to like the video and subscribe to the channel. It helps me to know which videos are helpful, and it helps other people to find these videos so that they can also get help. Thank you.